So in this video, we are going to discuss about binary search. So the idea of the binary search is it divides the sorted collection in half until the sought for item is found or until it is determined that the item isn't in the collection. Okay, so that's why it's called as binary, because you recursively divide the sets in two until we find the item that we are looking for. So here's the procedure for the binary search. So I will discuss this pseudocode as we go through an example as well. Okay, so the binary search na procedure has two inputs. The first one is the integer x, or the number that we are looking for, and another set of increasing the integers a sub 1 to a sub n. So in other words, the set is already sorted. Okay, so suppose that we are looking for a number 14, and we have a set of increasing integers 2, 4, until 20. Okay, so you can see that these numbers are in increasing order. So we set the first element as a sub 1, the second element 4 as a sub 2, third element 6 as a sub 3, and so forth. Okay, so the first thing is we have the initialization. We set I is equal to 1. So we will start with the first element in the list, or the first position in the list, and another index j, or another index j as the last element in the list. Okay, so we have I equals 1, or the location of the first element, and j equals 10 as the location of the last element. So next is we are going to compare the two. So this will be our terminating the condition. So while I is still less than j, then we will continue dividing the set. Okay, so first, since I is less than j, so we compute this process, or we proceed with this process. So we have I plus j divided by 2 and set that as m. So we are basically looking for the median, or the middle of the list. So we have 1 plus 10 divided by 2, and that will give us the median. M is equal to 5. Now, we will compare if the x, or the number that we are looking for, is greater than the number in the middle of the list. Then we set I equals m plus 1. Okay, so that would be m, which is 5 plus 1. So the new index I will now be in a sub 6. Okay, did you get it? So from initially we have the I here, but then 10 is less than 14. Okay, or 14 is greater than 10, or the middle of the list. So it's most likely that the number that we are looking for is between this, or within this list. Okay, so we totally discard the other half of the list. Okay, now the new index I is equal to m plus 1, or the middle plus middle of the list plus the location of the middle number plus 1. We now have I equals 6. Now, oops, we have not discussed this else j equals m. So else j equals m, that means that the location of the list is on the first half and not the second half. Okay, we will see that in the next example. Okay, now we have the new i's and j's. The I is now equal to 6 and j is equal to 10. Okay, now we are going to compute for the middle. Again, look for the middle element. So that will be 6 plus 10 divided by 2. That will give us 8. So meaning this is the middle of the list. So a sub 8. Now we are going to compare the number that we are looking for with the number in the middle of the list, which is 16. So we can see that the x is less than 16. So that means that j now will be equal to m. So meaning, yung nangyari is that since 14 is less than 16, so it's most likely that the list is, or the number is between 12, 14, and 16. Okay, so we discard the other half of the list and focus on the first half of this list. Okay, now we have a new updated I equals 6 and j equals 8. And the next is we are going to compute or look for the middle element again. So 6 plus 8 divided by 2, that will give us 7. And we have 14. Okay, and since the middle element is equal to 14, then we end the process. Okay, so that means that the location is 7. Now we have another example. Suppose we are looking for x equals 15. So we are going to divide the we are going to set the initial conditions I equals 1 and j equals 10, or the first and the last in the list. And next we are going to divide the list by looking for the middle element and compare the middle element with the number that we are looking for. Since 15 is greater than 5, then we will discard the first half and focus on the second half, because it's most likely that the number is in the second half. Now, the I now will now be I will now be equal to 6. Okay, and next is we have new i's and j's. So we are going to look for the middle element again, and the middle element is 8, which is computed from 6 plus 10 divided by 8. Okay, and we are going to compare the middle element with the x. So since 15 is less than 16, then that means that we are going to discard the other half and focus on the first half of this list. Okay, and we have another updated the i's and j's, and we are going to look for the middle element again. Compare, and since 14 is less than 15, so discard the other half, and the new na I will be equal to 8. So since we have not found the element, then the location is 0, or it's not on the list. Okay, so binary search adds a small complexity for large performance na games. And how long does it take for the binary search to run? So the worst case is, let's say if the list has 8 elements, it takes 3 steps. If the list has 16 elements, it takes 4 steps. If the list has 64 elements, it takes 6 steps. And if the list has n elements, it will be equal to log of n steps. Okay, so in some cases, doing a preliminary sorting of the collection can help make the search faster, as you have seen in the example of the binary search. But there are also costs for maintaining a sorted collection, especially if you have frequent insertions or deletion. So in the next videos, we are going to discuss about the sorting algorithms.